signal frequency domain spectrum S omega 1 omega 2 is a sum of 4 terms, cosine cosine transform minus sine sine transform plus I times cosine sine transform plus sine cosine transform. If I want to compute what will be the signal in the minus omega 1 plus omega 2 domain, I have to just change the sign of the frequency in that domain, and you will get this, because this sign, the cosine function is an even function, the sine function being an odd function, that will change sign here, and that will change sign here. If I want minus omega 2, then this is the quantity, and it turns out that this is exactly is a complex conjugate of this function. Okay. So if we have started with a real function, we get this, the S omega 1 minus omega 2 is complex conjugate of S minus omega 1 plus omega 2. And S minus omega 1 minus omega 2 is the complex conjugate of S plus omega 1 plus omega 2. So if we start with a single detected function signal here, then we really have information in 2 quadrants of omega 1 omega 2, and there is no additional information in the remaining 2 quadrants. What it means is that if we've done single channel detection in T2 domain, we don't have quadrature information in T2 domain. That's clear. But since Fourier transform is a complex transform, we have quadrature information in omega 1 domain. So plus omega 1 minus omega 1 signals are different, while plus omega 2 minus omega 2 signals are not different. This operation I have also here pictorially. Okay, what we had done was we had collected several sets of time domain signals, a free induction decay in time domain T2, and several of them which have a T1 variable in them. Then we did first Fourier transform with respect to time domain T2, and we get a complex transform, so we get a real part and the imaginary part. And if we have n2 data points in time domain T2, we get n2 by 2 real and n2 by 2 imaginary data points, cosine and sine. Okay, and then we do a Fourier transform with respect to T1 for the real as well as for the imaginary, and again we have a complex Fourier transform, so we get 4 different signals: the real, the real imaginary, and the imaginary real and imaginary imaginary. And these can be then combined into exactly the same way as I have written them there. It's pictorially represented by algebra. The only additional information here seems to be that you have, if you start with n1, n2 points, you get n1 by 2 and n2 by 2 points from which you have to construct your data information. All right, now we should look at the line shapes in 2D spectra. And the line shapes in 2D are in general complex. What that means is we will see soon, okay, that and this at this point I again go back and substitute the T2, otherwise I cannot do Fourier transform. This is necessary, otherwise I cannot do Fourier transform. The signal must decay. And since the signal has 0 before t for times less than t equal to 0, I can put a 0 here. And this is substituted from previous equation. And when I do the Fourier transform, then we get what's called as an absorptive signal minus the dispersive signal into absorptive and dispersive in time domain T2, or frequency domain T2, and this is in frequency domain omega 1, omega 2, where A is the absorptive Lorentzian, because this is an exponential signal. Its Fourier transform is a Lorentzian, which is given by this. And the dispersive Lorentzian is here. So since we had an exponentially decaying function, exponentially decaying time domain signal, which we had actually phenomenologically put down there, we did not really derive this. We just said, oh, it's exponentially decaying. So the line shape that I am saying is that it is Lorentzian is by phenomenologically, just saying that it's going to be Lorentzian. We assume that. Okay, it so happens that the signal in liquids, weakly interacting systems, are generally Lorentzian. In solids, they are generally Gaussian. Okay, So we will have terms with A in one domain and A in two domain. There's a pure absorptive in both omega 1 and omega 2. We'll have terms DD, which is purely dispersive in omega 1 and omega 2. We have A and D terms, which are mixed, and D and A terms, A and D terms, which are mixed in omega 1 and omega 2 domains. So we can have pure absorptive, we can have pure dispersive, or we can have mixed. In general, we get complicated line shape, and we have to sort out how to get line shapes which are not mixed. Okay, then we have this other complication, that the amplitude is also in general complex. Okay, ZKLM, KLMN is in general complex, but we can see from the operators that we have written down that KLMN is complex conjugate of ZLKNM. What that means is that this is complex conjugate of that, and this is the complex conjugate of that. Okay. So I have written down the previous expression from the previous page, and written down that we have terms like AA, DD, AD, and DA. Now I do a little trick and add signals from plus omega 1 and minus omega 1 domain. Okay, and then when I do that, I collect terms like this. You see, what I've done here is KLMN plus ZKLNM, and the second set of subscript define my frequency in the T1 domain. The first pair of subscripts define my frequency in the omega 2 domain. Okay, so what I'm saying is, let me take the amplitude of a signal which has a frequency KL in T2 and has frequency MN in T1, and add to it from the signal from the opposite quadrant. Okay, and then this is this. It will be that see since the absorptive part is symmetric, therefore I get this signal. Dispersive part is antisymmetric, and therefore I get a negative sign there. Okay, and if I do this, recombine these terms, then I see a separate coefficient for absorptive term, a separate coefficient for dispersive term, a separate coefficient for absorptive dispersive and dispersive absorptive. And okay, now I can say that I am going to plot the real part of this signal, S omega 1 omega 2, or the imaginary part, and this can yield what's called a phase sensitive spectrum. Or I can just compute the absolute value. That's what we did in the beginning, but it turned out that absolute value has mixed absorption dispersion, Lorentzian dispersion have long tails, and so the resolution is very bad. Okay, and it is very desirable to try to obtain a pure phase spectrum and then try to plot the absorptive part of the pure phase spectrum. Okay, for example, the real part of S omega 1 omega 2, the real part of S omega 1 omega 2 is given by this, where A is the real part of ZKLMN plus ZKLNM. The B is the real part of ZKLMN and ZKLNM. So I just pulled out the real part from the previous expression, and this is then defined coefficients A, B, C, and D. Okay, and so if I have a spectrum and I take the real part of ZKLMN and KLMN and KLNM, that is the frequency in plus omega 1 and minus omega 1, add them together, and there I get A. I subtract those two amplitudes, I get B. Okay, and then so on. And then the imaginary part, I get C and D. And these amplitudes tell me how much is the pure absorptive, how much is pure dispersive in the real part of S omega 1 omega 2. There are special cases, and this is where the interesting thing is. If we do a COSY with the 90Y, 90X and do a X detection, then it turns out Z, K, L, M, N are all real. Okay, it's very easy. I have just put real matrices in that and avoided I's. Okay, and then in that case the C and D are 0, and I will have either pure absorptive or pure dispersive, And this is indeed true that if ZKL-Mn is equal to ZKL-Nm, then B is equal to 0, and I have a pure absorptive signal. And this is what happens to a cross peak in a cozy experiment if you do it this way. The cross peak will be pure absorptive. And the diagonal peak are purely dispersive in this case. Okay. But if you have, this is true only for weakly coupled cases. If you have strong coupling, the second order coupling is present in the spectrum, then in general ZKL-Mn is not equal to ZKL-Nm. That is, the amplitude in plus omega 1 is not equal to plus minus times the amplitude in the minus omega 1 at the omega 2 frequency. And so then you have mixed phase automatically. You can't do much about it. All right. Let's see how we can then get out only the pure part of it. This is okay. We have at this stage of the Fourier transform, let me show you, at this stage of the Fourier transform, at this point, what we have is ST1 omega 2 after first Fourier transform, before the second Fourier transform. And if I am looking at this part of the data, then this is given by ST1 omega 2. Okay, because I had taken only the one channel, one detection in T2. I'm not doing quadrature in T2. So, and I want to see quadrature in T1. That's why we are looking at it at this point. Now, if we have the signal and we do a cosine transform with respect to T1, then we will overlap plus omega 1 and minus omega 1 domain. Okay, and what we are going to compute if just we do a pure cosine transform on the signal. So we will have a omega 1 which is sum of omega 1 plus omega 1 and minus omega 1. If we do a sine transform, we will subtract the two. Okay. And to obtain that, that means if we have ZKL-Mn is equal to plus times ZKL-Nm, the two amplitudes in two quadrants are equal. This means this signal was a cosine modulated signal. Okay. And only in that circumstance I will have ZKL-Mn equal to ZKL-Nm. It's a cosine modulated signal. And if I do a cosine transform, I'll get a pure absorption. On the same signal, if I do a sine transform, I'll get a pure dispersion. On the other hand, if ZKL-Mn is minus times ZKL-Nm, then it is a sine modulated signal. This signal is a sine modulated signal. And on that, if I do a cosine transform, again I'll get pure dispersive. But if I do a sine transform on a sine modulated signal, I'll get pure absorptive. So this table provides you the recipe. If you know whether you have a cosine modulated signal or sine modulated signal, what you should do to get the pure absorptive signal. However, there are often situations like this, that we have signal only in one quadrant and nothing in the other. Okay. That means all the signal is restricted to, I guess I can use any, okay. All the signal is restricted to, say, in this area. And there is nothing here. It is actually a phase modulated signal. Okay. It's a phase modulated signal. It's a mixed phase. And you can't get pure phase out of it unless you supplement the data that you have collected and convert a phase modulation into an amplitude modulation. This is what happens in resolved spectroscopy. In the ROSY, we get phase modulated signal. Okay. And then you have to do another experiment and supplement it with a experiment which will give us data in this domain, and then we get an amplitude modulated signal, and we can convert it into a pure absorptive signal. Okay. And so this can be supplemented with a quadrature data set. And that means if this kind of thing happens, then you must start with the quadrature data set. Okay. And I have here pure phase highly desirable because absorption mode has high resolution. I like to show you some of these line shapes. These are from book of Richard Ernst, and what will be the transparency on a slightly pinkish background. I think you can see them. This is the purely absorptive signal in the two time domains, both absorptive in both omega 1 and omega 2. In the contour plot form it looks like this, in a stacked plot form it looks like this. This is purely dispersive signal in both omega 1 and omega 2 domain, and it somewhat looks like this, which has a positive values here and negative lobes here, and this is a big slang shape. Okay, and this I have shown here also, like that. Now, if you have, for example, it is summarizing pictorially what I said before, that if you have a situation that ZKLMN is equal to ZKLNM, then you have exactly identical signal in both the domains. Okay, and A is not equal to 0, B is equal to 0, and if you do a cosine transform of that, you will get a pure absorptive, because you are overlapping this with this. You are adding these two, and when you add these two, the dispersive component cancels out. On the other hand, you may have this situation where there is a minus sign here, A is equal to 0 and B not equal to 0, and when you add these two, you get pure dispersive. But if you do a sign transform on this, you will get pure absorptive. Okay, but if you did a sign transform of this, you will get pure dispersive. Now, a word about quadrature detection. We are familiar with quadrature detection in 1D NMR, but I review it. Okay, and then when we do a single channel detection in 1D NMR, we have a signal time domain signal which is only a real part. Okay, and we do a complex Fourier transform in that, we get a complex signal which is defining my plus omega domain. The minus omega domain has no new information, because minus omega has P star which is no new information. Okay, so single channel will not give you information about whether the signal is in above the carrier or below the carrier. Okay, the plus minus omega are not distinct, they have same data. But if you do a quadrature detection, that means you have a real part and an imaginary part. What is quadrature detection there in 1D NMR is that you have two detectors which are 90 degree out of phase. Okay, so you are actually, you use only one detector, you just phase shift the other detector by 90 degrees. And phase shift is nothing but a time delay. We will also see that, that's interesting. Okay, so you have, basically you have data in quadrature, you have two data sets, and then they can very easily see whether you have a positive frequency or a negative frequency. And basically says P and Q are different information. So you can distinguish plus minus omega domain. In two-dimensional NMR, you can do single channel in T2. That's what we till now said, and we came to the conclusion that we have different information. We have, even when we do single channel in T2, we get quadrature information along omega 1, but no quadrature information along omega 2. Okay, this was our conclusion up till now. Now, when we try to do quadrature in T2, then our time domain data is still complex. It's not just one set, we have two sets. And hopefully they are in quadrature, that means 90 degree out of phase with each other. If you do not collect 90 degree out of phase, you collect 100 degree out of phase, it's not going to help. So you must collect 90 degree out of phase. And so it must be a complex signal. And we can represent two parts of it by a real part and imaginary part, and then a complex Fourier transform in 2D, and then we get more complicated looking total signal, total spectrum, which has a real part, which is sum of 4 terms, where cos of real part, sin of real part, cos sin of imaginary part, and sin cos of imaginary part, and imaginary part, which is again sum of 4 terms. And if you now compute the 4 quadrants of omega 1, omega 2 have completely different information, okay, which is given by here. And there is a notation here that which first cos refers to first omega 1 or T1 domain, and second refers to the omega 2. And one has to be a bit careful with this, because if we again write 1 and 2 here, it becomes too much. So just we follow this first one first, the second one second. Simple. Okay, so this is basically what we have about how we collect time domain data, how we process it, and what kind of line shapes we get, and in two-dimensional NMR spectroscopy. We come to a more mundane matter as to plotting of 2D spectra. It looks mundane from the point of view of you don't have to do much calculation at the moment, but it is very important how you do it. One can simply do an absolute intensity mode, okay, and not worry about it. Calculate the absolute intensity of P, Q, R, and S, and you have different information in the 4 quadrants, but the phase information is lost, and we'll get mixed line shape and broad lines if you have mixed line shape phases. You can do a phase sensitive mode and plot either the real or the imaginary part of P, Q, R, S, and depending upon what kind of modulated signal you have, you can get pure absorptive or pure dispersive, and the information content is higher because you know whether the line is going to be plus or minus, absorptive or dispersive. These are all equations. We can do it with